Hi there, Miss Barber here. This lesson is called Propositions and Truth Values. The learning objectives for this lesson are 1. Identify propositions and write their negations. 2. Complete truth tables and determine logical equivalence. 3. Determine the truth values of conjunctions and disjunctions. 4. Interpret or statements as inclusive or exclusive. 5. Determine truth values of conditional propositions. And 6. Rephrase converse, inverse, and contrapositive statements. Before we proceed, let's get some definitions out of the way. A proposition makes a claim, either an assertion or a denial, that may be either true or false. It must have the structure of a complete sentence. Any proposition has two possible truth values, true or false. A truth table is a table with a row for each possible set of truth values for the propositions being considered. Example, negation. Write the negation of the proposition, Charlene earned her bachelor's degree last year. For the solution, the negation of the proposition is Charlene did not earn her bachelor's degree last year. If the negation is false, the original statement must be true, meaning that Charlene indeed earned her bachelor's degree last year. Double negation. The double negation of a proposition P, read not P, has the same truth value as P. Provided for you is a truth table. Let's observe it has 3 columns in 3 rows. The first column is labeled P, that's our statement's truth value. The second column is labeled not P, that's the negation of the statement's truth value. And the third one is not P, which is the truth value of the negation of the original truth value. So going to the second row, if the truth value is true, the negation not P is false, and the double negation would be true. Now for the statement P, third column, if the truth value is false, then the negation would be true, and the negation of the negation is false. Make sure that you take the time to know this table by heart. Example with double negation. After reviewing data showing an association between low-level radiation and cancer among older workers at the Oak Ridge National Laboratory, a health scientist from the University of North Carolina, Chapel Hill, was asked about the possibility of a similar association among younger workers at another national laboratory. He was quoted as saying in the Boulder Daily Camera, "My opinion is that it's unlikely that there is no association." Does the scientist think there is an association between low-level radiation and cancer among younger workers? Analysis. Because of the words unlikely and no association, the scientist's statement contains a double negation. P is the statement, it is likely that there is an association between low-level radiation and cancer. The word unlikely gives us the statement that it's unlikely that there is an association, which identify as not P. The words no association transform this last statement into the original statement, it's unlikely that there is no association, which we recognize as not P. And so what's the gist of this? The conclusion. Double negation has the same truth value as the original proposition. We conclude that the scientist believes it's likely that there is an association between low-level radiation and cancer among younger workers. On to logical connectors. Propositions are often joined with logical connectors. Words such as and, or, and if-then. For example, let P be the statement, I ate the cookie, and Q be the statement, it was good. We'll make a new proposition using the logical connectors, and. So the new proposition is, I ate the cookie, and it was good. Or I could use the logical connector, or. I ate the cookie, or it was good. And finally, if then. If I ate the cookie, then it was good. The and statements, or conjunctions, given two propositions P and Q, the statement P and Q is called their conjunction. It is true only if P and Q are both true. Let's look at the truth table definition. We have a table with 3 columns and 5 rows. The first column is labeled P, and possible truth values in that column are TT, FF. The second column is Q, and the truth values for Q in that column are TF, TF, and the third column is labeled P and Q. Now we'll read horizontally. If we are looking at P and Q in the first row with the truth values, true and true is defined as true. Let's observe that the last 3 rows contain at least one F, or false. For example, true and false and true, and false. All 3 of these have the conjunction truth value of false. It is important to know this truth value table by heart. The symbol for conjunction looks like an upside down V. Example, and statements. Part A, the capital of France is Paris, and Antarctica is cold. Solution. The statement contains 2 distinct propositions. We'll let P equal the proposition, the capital of France is Paris, and Q be the proposition, Antarctica is cold. Symbolically, we could write P conjunction Q. And now we conclude, because both propositions are true, their conjunction is also true. That is, T and T equals T. Truth and truth equals the truth. Part B. The capital of France is Paris, and the capital of America is Madrid. The statement contains 2 distinct propositions. P will let be the statement, the capital of France is Paris, and Q the proposition, the capital of America is Madrid. Symbolically, we would write P conjunction Q. Now let's observe, although the first proposition is true, the second is false. Therefore, the conjunction is also false. That is, symbolically we know T and F equals F. That is, truth and false equals false. 2 types of or. The word or can be interpreted in 2 distinct ways. An inclusive or means either or both. Consider, would you like cake or ice cream or both? An exclusive or means one or the other, but not both. Would you like to go swimming or stay home? You can do one or the other, but not both. In logic, we assume that or is inclusive unless otherwise explicitly stated. The logic of or. Disjunctions. Given 2 propositions P and Q, the statement P or Q is called their disjunction. It is true unless P and Q are both false. Let's consider the truth table, 3 columns, 5 lines. The first column is labeled P, followed by the possible truth values of TT, FF. Second column is labeled Q. The possible truth values in that column are TF, TF, and the third column is labeled P or Q, that is the disjunction. Now let's read horizontally, starting in the first row of truth values. T or T is T, that is truth or truth is true. Now let's observe the next row of truth values. True or false, the disjunction is also true. The third row, false or true, the disjunction is also true. And finally, let's look at the fourth row. False or false is false. Let's observe that in a disjunction, as long as one proposition is true, that disjunction is true. This is worthy of you to know by heart. The symbol for disjunction looks like V. Example, or statement. Consider the statement, airplanes can fly or cows can read. Is the statement true? For the solution, let's consider. The statement is a disjunction of two propositions. The propositions are 1, airplanes can fly, and 2, cows can read. The first proposition is clearly true, while the second is clearly false, which makes the disjunction P or Q true. That is, the statement, airplanes can fly or cows can read, is true. The logic of if-then statements. These are called conditionals. A statement of the form, if P, then Q, is called a conditional proposition or implication. It is true unless P is true and Q is false. Presented here is a truth table of 3 columns and 5 rows. The first column is P, the second column is Q, the third column is titled If P, Then Q. Let's read horizontally. Starting with the first row of truth values, we have true, true. That is, if true, then true. That implication is true. Let's look at the second row of truth values. If true, then false. Then that implication is false. Now let's observe, this is rather interesting, both the third and the fourth row. If false then true, that implication is true. And finally, the last one, if false, then that implication is true. Now let's consider a statement here and say P is a statement you promised your friend that you would pick him up at the airport, and Q is the statement that you did. So on the first row, you promised to pick him up and you pick him up. That's good, that's true. However, if you promise to pick him up, so now we're looking at the second row, and you don't, that conditional proposition is a false. It's a bad thing for you to say you're going to do something and you don't. Now, let's apply that to the third and fourth. If you say you're not going to pick him up, but you do anyway, that's a good thing. And so that's a true for conditional proposition. And finally, if you say you're not going to pick him up and you don't pick him up, that's okay too. That is a true conditional proposition. This implication table needs to be memorized. Proposition P is called the hypothesis. Proposition Q is called the conclusion. Alternative phrasings of conditionals. The following are common alternative ways of stating if P, then Q. P is sufficient for Q. P will lead to Q. P implies Q. Q is necessary for P. Q if P. Q whenever P. To ensure your understanding, write the common alternative ways of saying, if it is my birthday, then I will have cake. Let's do this together, starting with P is sufficient for Q. My birthday is sufficient for cake. The second one, my birthday will lead to cake. Third, my birthday implies I will have cake. Now let's go to the second column. Q is necessary for P. Cake is necessary for my birthday. Q if P. Cake if it is my birthday. And finally, Q whenever P. I will have cake whenever it is my birthday. We have 3 common variations on the conditional. Consider the conditional, or the implication, if P, then Q. Let's add some context. So for example, if it is raining, then I will bring an umbrella to work. The converse, of if P then Q is if Q then P. If I bring an umbrella to work, then it must be raining. The inverse of if P then Q is if not P, then not Q. So rewriting the conditional, if it is not raining, then I will not bring an umbrella to work. And finally, the contrapositive for if P then Q is if not Q, then not P. The contrapositive statement is if I do not bring an umbrella to work, then it must not be raining. The conditionals and their variations, that's if P then Q, and the converse, inverse, and contrapositive need to be memorized. Logical equivalence. Two statements are logically equivalent if they share the same truth values. Let's observe the truth tables and the values for the implication, the converse, the inverse, and the contrapositive. Let's note the conditional and the contrapositive are logically equivalent. That is, the columns are T, F, T, T. They are identical. Now, let's look at the columns for converse and inverse. Let's observe the columns are T, T, F, T for both. That is, converse and inverse are logically equivalent. Example, logical equivalence. Consider the true statement, if a creature is a whale, then it is a mammal. Write its converse, inverse, and contrapositive. Evaluate the truth of each statement. Which statements are logically equivalent? Let's begin for the solution. The statement has the form if P then Q, and we'll say that's where P equals a creature is a whale, that's the proposition, and Q will be the statement a creature is a mammal. The converse is if Q then P. So rewritten, it'll be if a creature is a mammal, then it is a whale. This statement is false because most mammals are not whales. Let's consider the inverse. If not P, then not Q. The statement becomes, if a creature is not a whale, then it is not a mammal. This statement is also false. For example, dogs are not whales, but they are mammals. Now let's observe that both the converse and the inverse are false when the original statement was true. Now let's look at the contrapositive. If not Q, then not P. If a creature is not a mammal, then it is not a whale. And like the original statement, this statement is true because all whales are mammals. Logical equivalence recap. Let's note and remember that the original proposition and its contrapositive have the same truth value and are logically equivalent. That means if the original proposition is true, then so is the contrapositive. Similarly, if the original proposition is false, then so is the contrapositive. And the converse and the inverse have the same truth value and are logically equivalent as well.